All right, so I wanted to go ahead and just give an update for something I've been working on. So this is my research project. Been on this for I want to say about a year, a couple years now. Can't remember how long I've been on this. But anyway, for the past 3 days, I've actually been trying to work really hard at implementing some very basic antenna models. So when you think about antenna, you got this particular, like, let's look at probably this one. Zoom in on it. So here you see this antenna. You got a main lobe and a back lobe and some side lobes. And what I'm basically, for this kind of antenna, you got like a directed antenna that you're trying to communicate with somebody over here. So if you see the mouse, anybody over here you're trying to communicate with, anybody up here you don't want to talk to, here you don't want to talk to, and here you probably don't want to talk to, but there's still some sort of back lobe that may be transmitting information at a higher decibel this way that you don't want people to hear. So that's a lot of this is it's very much um, based on the geometry of the antenna that you're using and some very complex physics. Um, so that's what I've actually spent all of this weekend, or Monday, Tuesday, and Wednesday. Actually, I've been spending all this time trying to implement something like that. So you see that directed antenna. Here's another directed antenna. Uh, Now, there's also such thing as an isotropic antenna. And isotropic, you see all 360 degrees around. It's got basically near unity for your antenna gain. An ideal isotropic antenna actually is a sphere, but we can't really implement a spherical antenna. It's just something that's not realistic or realizable. So we actually can implement isotropic that's like this by using a dipole antenna, otherwise known as a whip antenna. But that's what we've actually been using, was one that's a sphere, and that's what we've been modeling in our project, is the sphere. I went ahead and implemented the directed antenna. Now you can see probably on this one here, you can see that it has this beam width here that they have by these blue lines. And what it's trying to say is that here you've got the peak, and then here you've got half power, which is about -3 decibels. So anything within this beam, within this angle in the forward facing vector of the antenna, of the directed antenna, you have communications on, and anything outside of this, you actually are not, you have unintended communication. You just say that you don't have communications. For our project, I prefer to try to implement the side lobes or the back plane, but until I can get a good method to actually implement it, what we have now is something that's like just the main lobe. So going back to this, you can see that here we have these blue, yellow, and green dots. These are the transmitters that are on the field. As you can see in this image, you can see farmland pretty much. That's how giant of a field we got. And then up here, these black missile-looking things are actually the receivers. So the receivers, we're trying to place them on this three-dimensional field in the most optimal position that the computer can come up with. And the computer's coming up with stuff that's based off of our priority weight. So each of these colors represents a priority of what they're receiving. There's also power. We want to make sure that we can actually hear them, which we can see down here that we actually printed out. You probably can't see it from that resolution. And there's also spread weight. We'll make sure they're not laying on top of each other. Distance, we want to make from the center of mass that they're actually able to, they're not going too far out, that it kind of pulls them in. That's a component I'm working on getting rid of until I'm trying to make something that's that we can get better solutions out of it by getting rid of distance. So we have that in there for now. And then there's also pheromones. You see on this two-dimensional screen this little dot that I haven't made it very well defined in a three-dimensional. It's actually right here, and I can barely make it out. That's attracting them and saying we want to make sure our solutions are closer to this area. All this was previously implemented, and what's new is the directional aspect of it. So before I actually had these as dots because they didn't have an orientation. Well, I added orientation to the PSO solution, so now when we run it, they're actually pointed towards the targets that they want to actually communicate with. So you see this guy here, he's pointed over there. We can look here and see that he's actually wanting to communicate with these guys, or he decided to receive those guys. Over here, this guy is pointed upwards, and this is about a 60. It's going to be a 60-degree spread, so I'm not sure what he's able to pick up. It's only going to be these guys over here, and then this guy's also pointed upwards, and he's able to communicate with these guys. So another aspect of this project that I forgot to mention is that our receivers also have a power limit. They can't receive too much power, otherwise they'll overload their feed horn and then it won't work. So we want to make sure that if the feed horn is overloaded, then we're going to say that that receiver is actually, we're going to shut it off so it doesn't blow it up. We want to make sure that when we optimize for our solutions, that it's able to pick up with respect to that feed horn not being overloaded. So it could be possible that this is the best angle that it can receive these. If it dips down too much, it may actually pick up too many assets on the same frequency and actually cause a feed horn to blow or something like that. So this is the optimized position that the PSO has found for each of these receivers to try to pick up as much of these transmitters that are on the ground. And you can see here the blue, yellow, and green are respective to the transmitter signals, frequency, and power. Then the underside has a pink bar. That's a negative dBm. That's the receiving side. That's the power that the receiver is actually picking up. So if we look at this guy over here that's pointed upwards, he's actually able to pick up one of the yellow ones, which looks like it's probably this one. It's got high enough power that it's very near 0 decibel on the receive side. So if you know your decibel math, 0 dB is actually the same thing as multiplying something by 1. So anything on a negative is like dividing by a number, and anything positive is multiplying by a number. So with 0 dB, he's actually picking up a lot from that yellow one, which is probably why he's pointed upwards to try to remove, lower some of that power so he doesn't overload his feed horn. So that's just an illustration of the project, and we can run it normal. So I was running it slow before, just to show, like, before this project was implemented, our sponsors actually used a program that took 7 minutes to actually calculate something way more basic than this. Right now, it takes seconds. So what that means is that if we had these connected to drones that were communicating with this computer went ahead and said these are the solutions, the places that the drone should be at, then it can communicate that to the drones and they fly to it. And then about a second later, it's actually able to come up with another solution and say, okay, now we're changing, fly over that way. So that it's able to update in real time. It used to be underneath a second because of how little we were actually paying attention to, but some of the things that I've actually added into this is we want to make sure to check line of sight. So we want to make sure that even if, like here, if it was to pop up here, it won't be able to communicate to these because there's a mountain in the way. On this particular this frequency range, there's no way they can communicate to through a mountain. So I implemented line of sight, and it blocks anything that's out of line of sight, and it's also trying to it pays attention to curvature of the earth. So adding all those as well as adding this directed antenna has actually slowed down the program tremendously. But even though it slowed it down, it's still very close to real time, and we're actually able to get reasonable solutions. Not highly repeatable, but they're actual reasonable solutions that if we wanted to just run it once, you get to a site, load up all the signals, and then run it once, and then we set ourselves to fly, and they fly to those particular positions. We know it's an optimized position. It's okay. So that's our research project, and yeah. So for the past 3 days, I've actually been working on getting that directed antenna built into the project, and it did it. It really didn't take too much work on the fitness and the PSO side, because all I had to actually do was increase our dimension spread. And so our potential solution here, it gets the transceiver object, it sets X, sets Y, sets Z, and then it sets the frequency. And now it also sets the antenna, which here we set the beam width. I only have it as constants down the program. You should never do this. Plan on putting that into the parameter file, so then we can set these directions for the X and the Y for the beam width. That very basic beam width that I implemented. And then here, the potential solution, once we got X, Y, Z and a frequency, we can also get the final three parts of it, which are the orientation and Cartesian coordinates. So then we apply this orientation to the forward vector of our antenna and we set the orientation of the antenna, and then we set our receiver on our receiver object. And with that new frequency, with that new antenna model. So then it's going to go through, and each time that it checks to assign the signals, so here we call assign signals, it'll go through all the signals. First it checks LOS as previously implemented, also still checks the distance, gets the path loss and applies that path loss. And now it's also going to add the antenna gain to that equation. So once you get into dB math, all you really got to do is do an addition. So basically, you get the receiver object, get its receiver, then you call its antenna and try to get the gain based off of that signal's position. So you just got to send it the signal, which is a transceiver object. Transceiver object inherits from a physical object, which has X, Y, Z, and orientation and all those things. So transceiver objects received, we get the position inside of here, and it tells whether or not that signal is within the beam width of that antenna. And if it is so, it'll return a parabolic interpolation from peak power to half power, as well as it estimates the antenna efficiency based off of the beam width. So that we have X and Y, it's gonna do some sort of geometric mean between the two and get the antenna gain that way. So that's applied, and then we do the rest of the clearing out if there's any problems, stuff like that. So yeah, that's the project that we've been working on for the past couple of years, and that's the antenna model that I just added. So now we can see that instead of those black dots we had before, we actually have these missile shapes that show the direction that they're pointing at, and it appears to be working correctly. I'm still kind of not too okay with it being so slow. I'm pretty sure there's probably a better way to actually optimize this program to make it run faster. But until I mean, it's not really part of the grant, so it's not something that I should work too much at it getting implemented. So when we pass this off to our sponsors, they can actually implement more realistic antenna models and probably work on optimizing it. But I've at least given them a starting point so they can actually go around and actually have a directed antenna, not just some isotropic idealistic antenna that doesn't really matter. So we can actually get really close to realistic solutions that they'll probably want. So that's the project. Hope you enjoy it.